All right. Hey, good evening, everyone. So this is our fourth part. So today we have Nico here. So Nico is a condensed matter theorist currently working towards his PhD under Professor David Vanderbilt. And in 2016, he graduated from the National Technology University of Athens with a fifth-year joint degree, specializing in theoretical physics and advanced material science. So he's currently interested in the field of topological materials. So his research revolves around classifying and predicting new topological materials, as well as exploring novel phenomena and applications of existing topological materials. And so, yeah, that's it. So please unmute yourself and let's give it up for Nico.
Thanks,
right.
Everyone.
Take it away, Nico.
Can you hear me?
Yeah, perfect.
Okay. So thanks, everyone, for coming tonight. Prepared to talk about the interpretation of quantum mechanics, and specifically I'm going to focus on the many worlds interpretation, or Everettian quantum mechanics. Feel free to stop me at any point. And basically, I wanted to give this talk because I didn't used to think that interpretations of quantum mechanics were like an important thing. You know, it's after all, we can't measure and distinguish them. So what is the point of learning and spending time? And slowly I realized there are many benefits. For once, I'm going to try to give you a sense that it helps you organize your knowledge, in the sense that you don't have these fragmented facts about quantum mechanics and when does this happen and so on and so forth. And that's because you realize what are the questions that are not what definitions are not well defined, like, for example, measurement, and what does measurement mean, and what is real in the wave function, what is epistemic and what's ontological, this kind of stuff. So it really helps you organize your knowledge. Secondly, now with the second quantum revolution, you know, we're building quantum computers, which means we are manipulating coherent quantum systems for long times. We will have to face the reality of defining this. What does measurement mean? What constitute the measurements? And this question will inevitably come, and we'll need to answer them. And finally, because in this, you know, we are PhD students, we are very focused on specializing on a very small subset of physics, and sometimes we forget the big picture. And at least I really enjoy physics because of the big picture, you know, and sometimes it's good to step back and look at what is the big picture of what we're doing. Okay, so yeah, the motivation of this talk is this book from Sean Carroll, which I recommend, Something Deeply Hidden, which talks about the interpretations of quantum mechanics, and he's also the proponent of many worlds interpretation. And so the talk is based on the book. Yes?
Can I ask a question?
Yeah.
So I'm always wondering, what is Everettian? Oh. What's that word? I never saw that.
Wait, I'm lagging. Sorry. Sorry, I didn't hear anything. Can you, now I'm connected again.
Oh, okay. Can you explain what is Everettian?
Yeah, Everett is the guy that proposed this interpretation of quantum mechanics. I'm gonna come to it. It was the student of Wigner at Princeton back in the 60s. But then he left academia because everyone was saying, oh, this is stupid, many worlds. But now it's like the second most famous interpretation after the Copenhagen. So I'll come to that. So Feynman famously said that I think I can safely say that nobody understands quantum mechanics. And he was referring to basically the measurements. Beside the measurement, quantum mechanics are pretty straightforward. There are a set of equations you can follow and make predictions, but the fact that we don't understand the measurement, so there's no consensus of what does the measurement means in quantum mechanics, shows that we don't really understand what's going on. And as physicists, we decided that this is maybe it's too hard to answer, so we should stop caring about it, and if everyone even discourage people that are interested in finding more about it. And Sean in his book has this, it says he reminds him of this fable from Aesopus, these famous fables where you have this fox and there is some grape on the top of of a tree, and because the fox tries to get the grapes and can't, it says to itself that, okay, probably the grapes are sour, so I don't even want them. So we have convinced ourselves we don't even want to find the solution. What does this mean? Because it's just too hard. But because it's hard, it shouldn't be a justification for that. So let me start by contrasting classical with quantum mechanics to see where the problem of this, the measurement problem emerges, okay? So in classical mechanics, we have Newton's equation, F equals ma, which is a deterministic equation that is given an initial configuration, an initial condition. We can predict the future arbitrarily. And quantum mechanics starts the same way. We have the Schrödinger equation. Again, it's a deterministic equation that tells us, given an initial wave function, how the system is going to evolve. So at this point, we have both of these theories are different, but when did the quantum mechanics came to be? When in the early 1900s, there were all these paradoxes with the Maxwell theory of electromagnetism. For example, if you consider an electron orbiting a nucleus, then and you use Newton's equation and input as the forces, the electromagnetic forces from Maxwell, then you predict that the electron will radiate energy and then collapse in the nucleus. And the solution to that came from the big physicists at the beginning of the quantum, the development of quantum mechanics, where they said, okay, we can fix this problem if we say that the electron is not a particle, but it's a wave that's given from the wave function. And then because the wave is gonna sit on its lowest energy level, then it's stable, doesn't radiate or collapse. And so and I'm showing here the orbitals, for example, for the hydrogen atoms. So this problem was solved by saying that the electron is a wave. But of course, we see particles in reality. For example, here you see a chunk of uranium, and if you put it in a cloud chamber, you just see particles coming out of the uranium. You don't see the waves that the quantum mechanics predict. If you use quantum mechanics, you'll find that you get these spherically symmetric waves expanding outwards. But that's not what we see. Our experience tells us that we see particles, not waves. And so then the second group of rules come, which is the so-called Copenhagen interpretation. This is what we learn in quantum mechanics textbooks. And there are three more axioms. It says that there are certain observable quantities, the physical observables, we can choose to measure. And when we do, we obtain definite results. The wave function associates an amplitude with every possible measurement outcome. And upon measurement, the wave function collapses. So here I show the wave before the measurement. It's a perfect wave, and then it collapses to a delta function, like if we say we measure the position. And so this is how we reconcile our experience that we see particle and not waves. Now, of course, it's not hard to see that the measurement is not well defined. There, for example, we can ask, what does it mean to observe or measure? How big has a measurement device have to be? How quickly does measurement happen? Does it need to be a human? Does it need to be conscious? Does it need to be able to encode information? You know, there's all these questions that the Copenhagen interpretation doesn't answer. We just, the problem is too hard and we avoid it because we never experience superposition, basically. We just see particles. And then the second group of not well-defined question is, what is a wave function? Does it represent reality? Is it only a part of reality? Is it our ignorance, or is it the truest sense? That's how nature works. And these are answerable questions. You know, they're hard, but they are answerable. So we can make progress on this, and the progress has been made. But before going there, let me just describe a little bit historically what happened in the famous 1927 Solvay conference, where all the big brains that were developing quantum mechanics were there. There were the famous Einstein-Bohr debates where they were discussing what does quantum mechanics mean. And Einstein was arguing that, you know, our duty is to understand what's going on, to interpret quantum mechanics, not just use it to calculate. But Niels Bohr was, you know, he was a proponent of this epistemic approach to quantum mechanics. So because we can make predictions, that's the job of quantum mechanics. We don't need to interpret it to be consistent. As long as it works, then that's it. And yeah, I mean, there is this famous how do you say, misconception that Einstein didn't like quantum mechanics, or, you know, he wasn't on the spooky action at a distance and so on. But in reality, he was asking the real question, like how can we make quantum mechanics well defined and like understand what's going on and not just hide our ignorance. And this brings us to the various interpretation of quantum mechanics. So basically, how from the mathematical theory of quantum mechanics, which is well defined, we got to the interpretation of the formalism and the phenomenology. So what does it mean? And here is a list from Wikipedia showing the most famous interpretations of quantum mechanics. The most famous is the Copenhagen interpretation, with 42% of physicists believing. Now, that was back in 2018, the poll, I think. And then the second one is the many worlds interpretation that I've been talking to, proposed by Hugh Everett. And you see, you have these columns that describe the different theories. So, for example, we'll have whether the theory is deterministic or not. Many worlds, it is deterministic, while the Copenhagen interpretation is not, because of the collapse of the wave function. We have whether the wave function is ontological. That means whether the wave function is a real thing or it describes our ignorance. But yeah, I guess it's better to talk first about what does the many world interpretation says, and then we can contrast them with other ones. And famously, David Mermin said, new interpretations appear every year, none ever disappear. And that's a valid concern, even though these are actually theories and they can be, they can be disproved. For example, the many worlds interpretation states that you always evolve unitarily with the Schrödinger equation. So if you can never find an instance where you don't evolve unitarily, then you can falsify the theory. And so these are not just philosophical, playing with words, but they're actual theories. Okay, so what is the Everett interpretation of quantum mechanics? So Everett the third, back in 1957, came with his thesis, the theory of the universal wave function, where he says, guys, chill, like, we don't need all these extra postulates about the measurement. We just have the wave function. The wave function represents the entire reality, and there is no collapse. It's just the Schrödinger equation, and it evolves unitarily. It's only our experience, as humans and as interacting beings, that makes us see that. So, well, in the Copenhagen interpretation, we had, when we are not looking, then the system evolves with the wave function, and when we are looking, we had the second set of rules where it explains how the measurement is done. In the Everettian approach, you just don't have these extra rules, and you try to derive them just from these two axioms. So, in that sense, the many worlds interpretation is the most elegant, the simplest, because it has the least assumptions. Just that the wave function is ontological and it obeys the Schrödinger equation. Okay, now it's the hard part, because we need to explain why do we see particles. This has to be derived from the theory. So the thing is that we can't pretend that we are classicals. That's what it has been always considered, that we have an observer and a quantum mechanical system, and the observer is classical and it observes the system. But in reality, everything is quantum mechanical. So the observers are quantum mechanical as well. And so another lesson is that there aren't separate wave functions for different systems. If we have two particles, then there is one wave function that describes the two particles. There's no two wave functions. Isolated systems, like, for example, an observer and the quantum mechanical system, it's an approximation. In reality, if you want to be the most accurate, there's only the wave function of the universe. There's just one wave function. It's just when some parts of the wave function are not interacting, we can call them isolated and talk about them. Okay, so we, the observers, are also quantum system. And the important thing here to understand, and this is not controversial, is that when the observer and the measuring device interact, they become entangled. So observation is entanglement. And to see that, there's a difference between interaction and measurement. You can interact without getting entangled, but when you observe, you're always entangled. For example, in the famous Stern-Gerlach experiment, when you throw this beam of electrons that are in this superposition of spin up and spin down, then each electron, one part of the wave function goes up and the other down, and then it collapses to either the up spot or the down spot, depending on, it's 50% probability. In this case, the measuring device becomes entangled with the spins because it interacts differently with different parts of the wave function. So the magnetic field interacts differently if your spin is up and when your spin is down. And that's what entanglement is. You interact differently with different parts of the wave function. And to contrast that with the gravitational field, so if you ever done, general relativity, there is this, the principle of equivalence, that you can't distinguish gravity in any experiment, because gravity interacts with everything the same way. There's no charge like that can be up or down. So gravity does not produce entanglement. So you can't use gravity to measure it. This was just to contrast what entanglement and interaction are.
So Nico,
Yeah.
you can interact without observing, but you cannot observe without interacting. Could that be right?
Yeah. You have to interact. So entanglement is like a stronger thing than interaction. Interaction is like a bigger set, and inside interaction there is entanglement.
Exactly. So
Yeah.
if you are entangling, you are interacting, but if you are interacting, you're not necessarily entangling.
Yeah. And the distinction is that you need to interact differently with different parts of the wave function. Like here we have,
if I think of forces, and if I think of like mediations of interaction, right? Like the photons, the potential graviton, gluons, that kind of stuff. Could there be a relationship in this between the specific particles? The fact that like the graviton has like a, what is it? Spin two.
Yeah.
And like it's a different field altogether, and like the interaction is just not an entangling interaction, whereas the photonic interaction is an entangling one.
So I mean, in general relativity, gravity, it's not a force. It describes how the space-time.
Yes, that's true.
Yeah. So in that sense, you can see that it doesn't.
And what is it? That the graviton is like an excitation of like perturbation of the.
I think it's just
of the
general
manifold.
relativity. It's not like
yeah.
It's a classical analog.
I think you're right. Yeah, and in that sense, gravity is very much different from all the other forces.
It's not a force in the real sense. So.
Cool.
Yeah, and actually, I realized that when I read this book, and it's so like fundamental, and that measurement always entangles, and entanglement is when you interact differently with different parts of the wave function. It's that's why I'm saying this kind of helps you organize your knowledge. Okay, so let's see the Schrödinger cat experiment in the Copenhagen interpretation to understand how we interpret things differently based on the two interpretations. So, in the famous experiment, thought experiment, we have the detector and some, let's say we can have again the Schrödinger experiment where we send one spin and 50% chance it goes up or down. And depending if it goes up, then nothing happens. But if it goes down, then we have a gas, and then it puts the cat to sleep. We don't have to kill here. We can put her to sleep. So that, before measuring what's going on, the cat should be in a position of being asleep and awake. And to see that, the cat is in a superposition of awake and asleep. And then we have the classical observer. So in the Copenhagen interpretations, observers are classical objects. And then the system collapses when the observer interacts with the quantum system to either the cat being awake and the observer seeing it being awake, or the cat being asleep and the observer seeing it being asleep. And here we use Niels Bohr because he was the proponent. Then in the Everettian quantum mechanics, then there's simply no collapse. So what happens when Everett opens the box to see if the cat is awake and alive, then Everett becomes also entangled with the system, and he's also being at the same time in a superposition of the cat being awake and he seeing it awake, and the cat being asleep and him seeing it asleep. So the puzzle is we don't ever feel like we're in a superposition. Why we don't feel like we're in a superposition? And this actually came after after Ever proposed his theory in the 60s, we understood this concept of decoherence, which means entanglement with the environment in the 80s, 70s and 80s. And this like paints a much like better picture of what's going on. Because as I told you, the only real thing is the wave function of the universe. Everything else is an approximation. So when we're talking about the experiment with the cat, we have to include the environment. Here it shows with the grass. And what the environment is all other degrees of freedom in the universe we don't keep track of, you know. The air inside the box or the everything else that it's not us. And this is from a presentation from Sean Carroll. And here, actually, I think this it doesn't necessarily need to be two things, but let's just, for the moment, follow his train of thought. So we, before the measurement, we have the quantum state of the cat, and then the observer and the environment that still have not interacted. But then inside the box, because the cat interacts with the air molecules, the light, and whatever, so on, then the cat becomes entangled with the environment. And what that does, you can show that mathematically, is that if you get entangled with the environment, then these two states do not get mixed by the forces of nature. So the matrix element is zero. So this state with the Hamiltonian gives you zero. So in this basis, we can say the Hamiltonian is diagonal because these two states do not interact. You know, they are orthogonal and they do not interact. And so because they do not interact, they can no longer affect each other. And so it's like they're two separate worlds. That's where the many worlds, the word worlds come from, because you have these two states that cannot interact because you have this macroscopical entanglement. And when you have a huge, like Hilbert space vector, then they can no longer interact. Just a comment on that, I think these two, the decoherence and the measurement, do not have to be separate. Basically, if you think of a quantum computer, decoherence comes when you measure. You just have a quantum system and then you measure, and at the same time you measure, you also decohere, you interact with the environment. But it's just a useful way to see it. So these two worlds are a convenient way to talk. But the real thing is that, you know, we have the real wave function has both of them. Okay, so how the many worlds appear. The two states in superposition are orthogonal and therefore evolve separately. In the future, they won't interact again. And why don't we feel that we are in a superposition? And I mean, you know, it sounds like a cynical answer, but there are literally two of you, and you can't distinguish one another. And because, as I said, they will never affect each other, it's like we have two separate worlds. Okay, so one of the questions one can answer is how probability then arise, you know? I mean, the theory is deterministically, right? You evolve unitarily with the Schrödinger equation, and then nothing else happens. But the question is, the probability arises when you ask, in which world am I in? So even if you know the exact wave function, you don't know in which part of the wave function you're in. And that's how probability emerges. I don't know if that makes sense. But it's basically here it's like Everett's doesn't know, have to ask in which part of these two states he's in, and he has to put some probability for that based on the rules. So for example, you can think of a quantum coin flip. So you have the spin that's a superposition of spin up and down, and you do 50 measurements. So you get a binary number with 50 digits based on whether you got spin up or spin down. And in some worlds, you'll be unlucky and you'll just get, all zeros. And in some other all ones, but in most worlds, you just get 50-50. So if you want to assign a probability, you have to say it's 50% chance I get spin up, 50%, and 50% chance I'll be in the other world and get. So here you see this equivalent thing, but with the branching of the universes. So you start and then you split. And here, after 4 flips, you have all these different universes. And in most universes, you have the distributions of, number of spin up and spin down. And based on that, using, Bayes' theorem, you can say you have to give a probability for where you landed. So this is like an argument for where the probability arises. And you can also show that it doesn't just work with the 1/2. It works with whatever. If you have 20-80 or 30-70%, it can still use the same argument. Okay, and then the last ingredient that came.
But Nico, so there would be there would be measurements all the time, right? If this is the real thing in the world, there would be an uncountable, unmeasurable, unknowable number of many worlds, right?
So Sean Carroll discussed that in his book. So there is a question if we have an infinite degrees of freedom in the universe. So that's the first question. If we have a finite degree of freedom, these measurements are not infinite. It's just a finite amount, but they could happen very fast. I think it's 10 to the minus 30. I know decoherence takes that much time. But this branching happens all the time, and if we have
you can think of like a block of like the Planck scale, a block of the size of a Planck scale.
Yeah.
How many of these are there in the universe? And each of them could have a measurement on it that could happen each Planck time.
Yeah.
So that's just a Google of Google.
Yeah, and the thing is that if it's finite degrees of freedom, sometimes this branching is gonna stop. That's where you arrive to the heat death of the universe. Nothing can interact anymore.
Yeah.
But this picture also describes the arrow of time. You can see that.
Yeah.
As time moves forward, you start branching.
Oh, that's cool.
Yeah. So. Yeah. I don't know. It's not completely satisfactory. This how the probabilities arises, and this is one of the biggest, criticisms towards the people are not satisfied with the explanations they have. So I give it a valid criticism towards that. But okay, the last ingredient that came at the beginning of the 2000s. That builds on this idea of decoherence. I don't know much about it, but I think it's very fascinating. It's this idea of quantum Darwinism. This idea, we want to explain how objective reality emerges. So why do we all agree that the spin is up and not like, okay, maybe I get spin up and you get spin down, but why is there objective reality? Why do we all agree that we get the same results? And very quickly, to give you an idea without going into details. So quantum mechanics tells us that any Hermitian operator is unobservable. It has real eigenvalues, and so it's observable. But the physical observables like position, momentum, polarization, current or whatever, this is a very small fraction of the possible Hermitian operators. And what he's saying is that the physical observables are the so-called fides observable, in the sense that they imprint their information, they copy themselves on the environment. So you can read the environment and read the value of these observables. So in this picture here, for example, you have your quantum system, and then you have the environment around it, this epsilon, and you can separate it into 8 parts. And just by measuring the environment, you can know what the value of this physical observable is for the systems, because they multiply, they copy their information everywhere in the environment. And this actually has been experimentally observed, and this is a very strong hypothesis that has been corroborated a lot to this point. If anyone's interested, I've put the paper here. It was developed by this guy Zurek, who also was a major developer the idea of decoherence. Okay, so just to show you how these questions of measurement start to become practical, there is this famous paradox called the Wigner's friends paradox, where there seems to be contradictions between observers, whether there was a measurement or not. So imagine that we have a box with a quantum system, like the Searle-Gerlach experiment, and we have the Wigner's friend inside the box and observes the measurement. And so you will assume that the wave function has collapsed. But what if the friend is inside another box, and for Wigner the wave function has not collapsed because he didn't look inside the box? So it looks like for the friend the wave function has collapsed, but for Wigner the wave function hasn't collapsed. And you can even generalize this thought experiment if you make more boxes and put more observers. So we can agree on objective facts. And I'm just mentioning this friends paradox because recently there have been actual experiments where they construct these systems. So for example, here we have the so-called extender friends paradox, where you have some qubit and then you have inside the box a system that can measure and save the information, and then outside you have another observer, and so you have these nested observers, and you can choose, for example, if you will measure inside the friend inside the box and then the other guy outside the box, and you make all sorts of correlation measurements. And you can test various interpretations, and some do, you get some like Bell inequalities and so on. But yeah, I don't want to go into detail. The idea is that you can build this quantum system where the idea of measurement no longer it's a well-defined thing. And with quantum computers, this is going to be even more prevalent as we go on. Okay, and one of the last things I'd like to say is that, the idea of measurement is built on particles, but particles are not always well defined. Like if you guys have done any quantum field theory, where we have, instead of wave functions of particles, we have wave functions of fields, then the particle is well defined if you have non-interacting fields. Then the particles are these excitations of the free fields. If you have weakly interacting fields, then you can also interpret what's going on using particles that interact through exchange of virtual particles, like in Feynman diagrams. But if you have strongly interacting fields, then this idea of particles breaks down. So it's like we know that our reality, it's not what we see, is that these fields interacting, this quantum field interacting, but because our experience is so strong, we can't accept it. But for me, it really helped me understand better quantum field theory as well, because you can see that the fields are the fundamental thing, and particle, it's only valid in some circumstances. Finally, this idea of looking at the wave function at its truest glory, the wave function of the universe, and trying to derive our experience. There are proponents that the thing that might help us actually find gravity. So we famously, what we do in quantum field theory, we get a classical theory and we quantize it, right? Quantum electrodynamics and so on. You take a classical theory and you quantize it, but that famously doesn't work with gravity. In reality, though, nature starts quantum mechanically, so from the wave function of the universe, and then you derive the classical theory. So what if we do that? Maybe we can find gravity. And there are actually new theories that believe that gravity is related to entropy. So entanglement entropy is by definition connected with energy, and there are also ways to find how to connect the geometry of space with entropy. And the geometry of real space with energy gives you general relativity. So maybe the only thing that exists is particles that become entangled, and that gives rise to gravity. For me, this is a very exciting idea, and I think there's been a lot of progress in the last years building on that. And finally, the way I see it is that in physics we use complex numbers, which we can't measure complex numbers, but it's in some sense the extension of real numbers, where all polynomials have roots, have a polynomial of degree and has n roots. In the same sense, in the Copenhagen interpretation, you just kill all these extra worlds because you don't observe them. But if you include them, then you get a much bigger theory that has the potential to give us more insight. And my final slide is about the meta issue. This is just me being speculative here, but that's how I see what's going on in science. So at the heart of the scientific methods, we have the experimental observation, right? We assume that we have an observer and a system, and we can apply measurements on the system and extract information about the universe and the world. And that's how we build science. But as we discussed, in quantum mechanics, measurement is entanglement. And when you have entanglement, then you can no longer describe the observer and the system different, as isolated. They become one thing. And the idea of many worlds is that it's our insistence of their independence, even though they're no longer independent, they're entangled, that makes us experience these single worlds. But the basic assumption of the scientific method breaks if you want to be real, because this assumption of the observer and the system is no longer true. It's just one thing. And I think as we try to understand more what that means for science, and this is going to help us in other ways too. For example, conscious beings they have, it's like we have this model of the universe in our brain. We make these simulations and we observe this universe, but you are also parts of yourself. And so there is this indistinction between observer and system, that the two become blurred, what is what, and that gives rise to the subjective experience. So I believe that as we learn more and try to understand these issues, this is going to help us understand better the hard problem of consciousness, what is AI, and all these interesting equations. And at least going to help us better define the questions we should ask. Because at this moment, we have many ill-defined things, and understanding the implication will be good for the future of the field. So thank you for taking the time, and can take questions now.
Thank you, Nico. Let's maybe unmute first and then give Nico a big hand. Excellent talk.
Yeah.
So yeah, please ask question if you have.
Nico,
Yeah.
I don't know if you did you go to Plumman's journal club, I think last week?
No, I missed it.
Okay. So he talked about this experiment about qubits and whether they maintain coherence, the information system, for some time, and they could show that their qubits were losing information while they were decohering because of cosmic rays.
Yeah, so the absolute.
So it makes me think of this a little bit. You're trying to have this tabletop experiment and to everything be contained, but the world is not.
Yeah.
A process in the upper atmosphere has just sent a muon to your tabletop. And maybe your proximity to it, since you're slightly radioactive and you're observing it, you might eject an alpha thing and destroy it. And you are now entangled with this own system, in the process of building these extremely quantum and tiny things, right?
Yeah, isolated.
Super isolated, but super sensitive. We've revealed their extremely entangled nature with the rest of the world.
Yeah.
So it's really cool. Yeah.
It's really cool. Yeah, and I guess it shows the need for the topological kind of computing, where you have robustness at it.
Yes. Yeah, that's true.
I have not as much as a question, but it's like an observation that the line of thought goes from a way to interpret the wave function, right? So one could conclude to the multiverse theory. So I was thinking, if we go the other way, assuming that such a multiverse exists, right, which is the different branching of possible outcomes, then the probability is an approximation of what we observe in this multiverse, right? So there would play it would be of some importance whether this multiverse is infinite or finite, because if it's finite, these probabilities we know as laws of quantum mechanics are just approximations, right? I mean, I'm trying to see it from like a more empirical, if one could call it empirical, like starting from the multiverse and building backwards the laws of quantum mechanics.
Yeah, I mean, that's the idea here. And this is, whether there are infinite universes or finite, it really depends on, the degrees of freedom. So famously, there is the black holes have a finite entropy, and you can associate entropy with degrees of freedom. And so that gives you, the smallest area, which is the Planck length that has 1 degree of freedom. Because there is like a finite mass, and you can see we have finite degrees of freedom. And that will mean that, I guess we'll just keep splitting. But I don't know, that wasn't connected to what you asked, but yeah.
Hey, Nico, I have a question.
Yeah.
Does, I don't know, well, I guess, so I don't know if, does Sean Carroll or anybody else that you've read talk about, like, basically talk about unitarity? Like, to me, it sounds like when you break something in two, like say you just do a measurement on spin up, spin down, that you've broken unitarity. And I heard him kind of hand wave in a popular interview a while back that, oh, you just, put in a factor that decreases the probabilities. But that sounds every bit as unintuitive as all the things he's arguing against. Does he talk about it?
Well, yeah. So the Schrödinger equation is unitary, right? So the measurement is what breaks unitarity. And in the Copenhagen interpretation, you just accept that measurement is a non-unitary operation.
Yeah.
But in the many worlds, there's no everything. We just have unitary time evolution. It's just our experience is that because we can't see all these extra worlds and we only experience this single world, that makes us think that measurement is non-unitary. But in reality, everything is unitarily evolved.
So then well, I guess, does that mean that thinking of it in terms of anything splitting off in the first place is wrong? Like you just have a wave function and it just goes?
Yeah. So if I go back to, these thought experiments here, so here, all of from decoherence to measurement, these are unitary things, it's just, take superpositions. So the coherence, measurement, everything is unitary. But because you just observe one of the two worlds, you think that, going from here to here, you broke unitarity. I don't know if that helps.
Yeah.
Something different.
Okay, thanks.
Hi, Nico. I have a quick question.
Hi.
What happens in a universe with no observers?
So I guess you just evolve unitarily. You just evolve with the Schrödinger equation. I mean, there's nobody to feel that they exist in a one world. These worlds is just a construction. They don't exist in some real sense. The only thing that exists is the wave function of the universe. It's just we being inside them. We've been, the way I see it, at least, that we were evolved to care about the things that we can interact with. Like, what's the point? I mean, you can only care and see and the things you will interact with. So all these extra things you cannot see. So if there's no observer, there is no need for these single worlds. It's just, you just have these waves, quantum mechanical wave interacting with each other.
Isn't that a great question though? Because I mean, you're putting your point to a great thing, Tom, because I mean, you talk about observers, but that's kind of putting the human being as a pedestal in like the whole universe. Why do we make observation? Like if there's no observers, there's still things around. Are these also observers in some way? Are just interaction observers?
Are particles observers?
Are particle observers?
My understanding is yes. And that's an issue we see in quantum computing where decoherence is caused when a particle, say a quasi-particle, comes in and ruins your qubit, like from a cosmic ray or something. That is an observation that's happening, is my understanding in quantum computing. I don't know if that jives with what you're saying, but that's...
The thing is that if you take this particle that, that belongs to the environment, and you don't take its degrees of freedom into account, then it is measurement, right? But if you take that particle and you say, okay, this particle is part of my system, then there's no measurement. It's just, your system plus this extra particle. And that's why I say it is our insistence that, you know, the particle and the system are independent that makes us live in one world, results in decoherence. It's so back to Tom's question, it's our insistence that we have separate system, and the insistence of an observer means that they I don't know, this is speculation, but it's the insistence of the observer that it's an isolated system. If you are a particle and you interact, then you just become entangled. There's no measurement. There needs to be someone that says, no, I have the system and I have the environment and they're separate. Then you have the coherence. I don't know if that makes sense.
I want to add on this whole observation thing from a standpoint of neuroscience and cognitive science, since Tom may agree with me, I don't know, is that what we perceive as a particle when we observe a quantum system is a pattern of our human brains or a nervous system that we call that a particle, or we call that anything. This is more of it's not a human-centered approach, it's more of a just reminding in the end of the day that many of these things are semantics that our human brains use to interpret things. At least that's how I see many of these philosophical questions is just questions of our existence, of our perception of the world. I don't know.
Mm-hmm.
I'm kind of thinking of like quantum fields and particles as just the same word for the same thing. It's a quantum field until we measure it, and in terms of measuring it, it turns into a particle to describe, and
yeah,
that's sort of my thinking. I'm not a physicist, so
yeah, these are.
But we sort of, there's this big, and what I know and the little that I know is that there's this big emphasis on the observation itself, and that somebody has to see the observation. And the other sort of question I had on top of that is that when do you have to see the observation? Could a particle interact and modify a quantum state, but then be detected an infinite of time later through a detector someplace else, and thus that qualifies as being observed? Or does the instantaneous interaction preclude anything that happens in the future?
So you don't have to see for the observation to happen. Like Tom said, you know, even a particle can measure if you don't consider it in your system. You know, anything can measure. The only way that you don't measure if you keep it isolated. If you have your quantum system in some environment that doesn't interact with anything else, which I mean it's incredibly hard to do. But if it interacts and then this information propagates through the environment, this is the decoherence. So if decoherence happens, then it's over. If your quantum system interacts with the environment and then the information like travels, then you just, the world split. You don't need consciousness. The observer is gonna feel that he's in one world, I guess.
So then the follow-up question to that is, how fast does that propagate? Because theoretically that propagates instantaneously.
Yeah, it's incredibly fast. It's 10 to the minus 30 seconds, the coherence occur. That means the quantum system has spread the information in the environment. So the coherence happens incredibly fast.
What kind of interaction is that? if you're saying decoherence spreads, I don't know that I understand what.
So in decoherence means entanglement with the environment. So, for example, think of a superposition of, let's say you have an electron here and here. You have in 2 points. Then the air molecule will interact differently if the electron is here or here. Then the other air molecule will interact differently. And this is like a tree, it spreads everywhere. It's just interactions, you know? And so depending on where the electron is, you get very different vectors in Hilbert space. And so that's what causes decoherence. The spreading, because depending on your initial position, it's like a butterfly effect, you know. That's what decoherence is.
Any more questions?
So can we go back to, you know, this is interesting for its own sake, but as far as understanding, let's say, predicting or understanding better quantum mechanics and the effects, definitely this is important for understanding quantum computers, correct?
Yeah.
If you have the perspective that you are also the system is an important part of the technology for the quantum computer. You are part of the system, so it means decoherence will happen inevitably unless you have it topologically protected. So that's kind of like conclusions I get from this.
Yeah. I mean, again, if you, for example, I think what they're trying to do in quantum computing is, you know, separate in energy some quantum levels, so that you need a big energy to excite something different. So, you know, but yeah, the idea here is to define what measurement is better. And I guess this is the Wigner paradox. For me, at least it was very illustrative, because, you know, you have two observers, but you can also observe the observer, you know. And in this experiment, the observer is a quantum mechanical system. That's what's cool. You can make observers like measuring devices that are quantum mechanical systems.
That's cool. Yeah.
Yeah, and like we're gonna use them, you know, in quantum computing.
I think also in quantum computing, that point you just mentioned, Victor, is if you take it far enough, it's kind of turtles all the way down. Like you need to, so like, you know, you put in an ancilla qubit, now all of a sudden that's part of your Hamiltonian. You put in a readout, that's part of your Hamiltonian then, and you put out some correction on the readout. And if at a certain point, hopefully it gets classical enough that you don't worry about it.
Yeah.
But in order to really accurately measure it, you know, you run into all those steps.
Yeah, which is really, that's why it's so difficult. I mean, getting really a quantum and maintaining quantum coherence and maintaining your qubit is very difficult.
Yeah.
So this is probably like a pretty basic question, but I just don't know. What are like the typical time scales of decoherence and, like, say, a very controlled system like a quantum computer?
Yeah, I don't know. Maybe Tom can help us.
So I was actually just at a talk yesterday where the University of Maryland group had a qubit with lifetimes around a millisecond. Mostly the sort of qubits that are in use by places like Google and IBM are in kind of the 70 microsecond range, in terms of if you just like sit them there for 70 microseconds, they'll lose their information in about that amount of time.
Wow.
And those are superconducting qubits. I know trapped atoms and similar things have much longer coherence times. It depends a lot on your system.
Thank you.
And technically, the topological qubit would be very large too, right?
Yeah, if it's done right, it would be infinite, but obviously.
Yeah, that's the point. That's the problem.
Okay.
That's the issue. Cool.
Any more comment or? Okay. If not, then thank you for this. Thank you, Nico, and thanks all for coming. And then yeah.
Thanks everyone.
Good luck, and
Nico.
then I'll see you somewhere.
Thank you, Nico.
Great work.
Bye.